Now in this class we are going to discuss few more results based on inner product space. One result I already written about. This result is called Pythagorean Theorem. What is Pythagorean Theorem in an inner product space? Suppose u and v are orthogonal vectors in V, means inner product of u comma v equal to 0. Then norm of u plus v whole square is nothing but sum of their square of the norm. Square of the sum of the norm is equal to sum of their norms of the corresponding vectors. Now here, now we are going to prove this result. This result is also called Pythagorean result. Okay. First we consider left hand side part. Consider norm of u plus v whole square. Yeah, you know that here already see norm of u is nothing but what? Square root of inner product of u comma u. But see me from that, what is norm of u square? Just inner product of u comma u, because you taken square root in the left hand side. Therefore, what is that? Inner product of u plus v comma u plus v. Now, I go for additivity of the first slot. You already know that V is a inner product space. From the condition of inner product space, it is force put additivity of the first slot. Now this can be written as inner product of u comma second component u plus v plus inner product of v comma u plus v. Additivity of the first slot. Yeah, we already proved that in note number 1 and 2 in the first class. Suppose V is an inner product space, additivity of the second slot also holds good. Therefore, from the additivity of the second slot, this can be written as inner product of u comma u plus inner product of u comma v. And also additivity of the second slot, this can be written inner product of v comma u plus inner product of v comma v. This is additivity of the second slot. Okay. Simply I written ASS, that is not standard abbreviations. Yeah. Inner product of u comma u. See, you know that u and v are since u and v are orthogonal vectors. Therefore, inner product of u comma v must be equal to inner product of v comma u must be equal to 0. Inner product of u comma v and inner product of v comma u must be 0. Therefore, these two must be 0 since u and v are orthogonal vectors. Only remaining inner product of v comma v. From the definition of norm, this is nothing but norm of u square plus this is nothing but norm of v square. This result is called Pythagorean theorem or Pythagorean result. Norm of u plus v whole square is equal to sum of square of the norm. That's all. We have moved to the next result. Yeah, this result frequently they are going to ask the question in the question paper. Result, this is also another one type of result. If V is a inner product space for a set of real numbers, or just you take R is an inner product space, then prove that for any vectors u, v belongs to capital V and any scalar C belongs to R, because here our scalar is set of real numbers. Then first one, positivity, yeah, This word is not given what you have a prescribed book. I refer some Google article. They given these results some name. They are mentioning positivity norm of u greater than 0 for u is not equal to 0. Second one, homogeneity is norm of C into U is nothing but C into norm of U. While taking this, we have taken absolute. Okay. C. Kaushi's quasi inequality. Cauchy's quasi inequality. Absolute of inner product of E comma V is less than or equal to norm of U into norm of V. Triangular inequality, last one. Inequality. Norm of U plus V is less than or equal to sum of their norms. Okay. Solution. Okay. Now we have to prove one by one. Yeah, first one is called positivity, second one homogeneity. These two name is not included in any textbook, but here I refer some article they given. Therefore, I'm mentioning some name. Cauchy-Schwarz inequality and triangular inequality. They may be asking any three in the exam for 6 or 7 marks. Okay. Now, what they given? V is a inner product space. Given V is an inner product space. Given V is a inner product space. Okay. First, I want to prove the first one. Now, I am consider norm of U square. What is norm of U square? Inner product of U comma U. Yeah, norm of U square is inner product is nothing but from the definition of norm, inner product of U comma U is nothing but what? U1 square plus U2 square, U3 square. Sum of each of the values is positive because even though U1, U2, U3 are negative, square of that is positive. Suppose U is having, simply I am going to take U1, U2, U3 like that. What is the inner product of U comma U is U1 square plus U2 square plus U3 square. Any one of the position value is negative, square of that is positive. Therefore, this is greater than this. What happened? This is greater than 0 for U is not equal to 0. Suppose U is 0, what happened? This inner product value is 0. Therefore, this is norm of U square is greater than 0 for U is not equal to 0. That implies norm of U greater than 0 for U is not equal to 0. I think it's clear everyone for this part. Norm U square is greater than 0, that implies norm of U is greater than 0 for U is not equal to 0. Suppose U is 0, this inner product value must be 0, 1. Next, I am going to take, what about that, consider the left hand side. Consider norm of CU. What is norm of CU from the definition? Inner product of CU, comma CU. Inner product of CU, comma CU. Now here we don't have a square root, therefore I am going to take a square root. Because keep in mind, norm of V is nothing but square root of inner product of V comma V. Okay. Norm V square is nothing but only inner product between V and V. Here we don't have a square root, therefore I take inside the square root. Yeah, square root of, from the what about homogeneity in the first slot, what we get? C. C into inner product of U comma CU. Again homogeneity for the second slot. This is the first slot, second slot. What do we get? Square root of c square into inner product of u comma u. Means homogeneity of first and second slots. Because you already know that V is an inner product space. From the definition of inner product space is satisfied homogeneity of the first slot, homogeneity of the second slot. Therefore, what we are going to do here, now we are taken c outside, twice we get c square. Root of c square, what we are going to return c. Then we have to take absolute of c, that's all, in root of what about that inner product of u comma u. What is that? Value is nothing but norm of u. That's all. Norm of u. Therefore, norm of cu can also be written as c. C they take an absolute value because once you take it outside inside the square root, then we have taken modulus. That's absolute value. Absolute of c is into norm of u. This is c is a what actually? Scalar. Yes. The next we are moved to the c. What is a c? Kaushi's Schwarz inequality. Absolute of norm of inner product of u comma v is less than or equal to norm of u, norm of v. This is as suppose v equal to 0, that implies LHS is equal to RHS. LHS is equal to RHS because v is 0, what happened? Inner product of u comma v. U comma inner product of u comma v, what happened? Inner product of u comma 0. What is that? 0. Similarly, norm of u into norm of v. What is that? Norm of u into norm of v is 0, we get 0. Therefore, v is equal to 0, LHS is equal to RHS. Less than or equal. Equality satisfied when v is equal to 0. Next, move to v is not equal to 0. Next, we are moving to v is not equal to. Assume that v equal to 0 is satisfied, LHS is equal to RHS. That satisfies the equality. Next, I have to prove that less than. Assume that v is not equal to 0. V is not equal to 0, we assume that. Now, I have to take let. I am choosing one vector, say alpha is nothing but inner product of uv divided by inner product of v comma v. I am choosing one vector. What's a vector? Alpha, inner product of u, just like a projection value divided by inner product of v comma projection of u on v. That's a v. Now I am choosing this. Then consider norm of u minus alpha into v whole square. Yeah. Consider norm of, because I want to prove this, inner product of u comma less than or equal to norm of u into norm of v. Norm of u minus alpha v whole square, where alpha is nothing but inner product of uv divided by inner product of v comma v. See, observe, you already know that norm of v square is equal to inner product of v comma v, means v1 square plus v2 square. Similarly, alpha minus u minus alpha v is again a vector. Norm of that means u1 square, u2 square, u3 square. Suppose this vector says w, you take the difference. Well, norm of w square is nothing but w1 square plus w2 square, w3 square. Each w1, w2 are negative or positive, square of that is positive. Therefore, this is must be greater than or equal to 0. The difference may be negative, may be positive, or may be a 0. That we get a vector. Then we are finding a norm. Square of the each of the components definitely is positive, is greater than or equal to 0. Next, we are going to simplify this from the definition of norm. This can be written as u minus alpha into v inner product, comma u minus alpha from the definition of norm. Definition of norm, we get this. And then again from the additivity of the first slot, or if I have to go for additivity, this can also be written as u plus of minus alpha into v, comma u plus of minus of alpha into v. Now I will go for additivity of the first slot. What we get? Inner product of u comma u plus of minus alpha into v, okay, plus inner product of minus alpha into v, comma, u plus of minus alpha into v. This is for additivity of the first slot. Move to additivity of the second slot. What do we get? Inner product of u comma u plus inner product of u comma minus alpha into v. Okay. And then similarly additivity of the second slot, inner product of minus alpha v comma u plus inner product of minus alpha v comma minus alpha into v. This is additivity of the second slot. Okay. Now I have to simplify that. Now move to homogeneity of the second slot. This can be written as minus alpha into inner product of u comma v. Again homogeneity of the first slot minus alpha into inner product of v comma u. Now here you take homogeneity of the first slot and homogeneity of the second slot. From both what we get? Minus alpha into minus alpha, we get minus alpha whole square v comma v. Homogeneity of first and second slots. Okay. Yeah, you know that what is the thing we want simplify further. Inner product of u comma u, okay, fine, minus alpha. What is alpha? Alpha is inner product of uv divided by v comma v. Yes, what we get? Inner product of u comma v whole square divided by v comma v. I am substituting alpha value. Here we get two terms because inner product of uv must be equal to vu from the symmetric because v is an inner product space. From the first property, symmetry, from the symmetry property, these two are same. I am taking twice of that. Minus of alpha square. What is alpha square? Inner product of uv whole square divided by v inner product of v comma v square into numerator having inner product of v comma v. What is the remaining? Inner product of v comma v. What's the remaining here? Inner product of u comma u, yes, minus same this is actually my plus, actually minus alpha whole square is alpha square, we get plus. These two are same. Denominator inner product of v comma v whole square is cancelled with numerator inner product of v comma v, we get this minus inner product of u comma v divided by inner product of v comma v. Yeah, we have to simplify further. Yes, I have to simplify further for this. What is right hand side here? Inner product norm of, what's the right hand side here? Norm of u minus alpha v whole square, okay, is greater than or equal to 0, and also this must be equal to what? This is actually inner product of u comma u, okay, minus inner product of, this is whole square, inner product of u comma v divided by inner product of v comma v. This implies 0. This must be equal to, this 0 is greater than or equal to inner product of u comma u minus inner product of u comma v divided by v comma v, because this is greater than or equal to 0 and this equal. Means this equal to this means this is this quantity, entire quantity is also greater than or equal to 0. This implies inner product of, this is whole square actually, inner product of u comma v whole square divided by, I shifted one of the term in the left hand side, is less than or equal to inner product of u comma u. That implies, take this as cross multiplication, we already taken v is not equal to 0, inner product of u comma v whole square is not less than or equal to inner product of u comma u into inner product of v comma v. Okay. From the definition of norm, inner product of u comma v whole square less than equal to, from that, this is norm u square into norm v square. That implies absolute of, because we are remove the squaring, taking a square root, absolute of inner product of u and v less than equal to norm of u into norm of. This is very important. Observe carefully. Yes, I think everyone is clear this part. What we taken, u minus alpha, norm of u minus alpha v whole square. This is greater than 0. You know that what is my alpha? Inner product of uv divided by inner product of v comma v. Now we simplify using the definition of norm. Simplify that. This quantity is greater than, means this is also greater than equal to 0. Shifted one other term in the right hand side. Simplify that. Finally we get absolute of inner product of u comma v is less than or equal to norm of u into norm of v. This is called Kaushi's quasi inequality. In the exam, not necessary to mention this result. They are going to ask, state and prove Kaushi's quasi inequality, triangular inequality. You must be know what's the result. What's the result of that inequality. Now let us move to the last one. Move to the last one. Last one is triangular inequality. Now, if you want to prove the triangular inequality, norm of u plus v, consider this part, norm of u plus v whole square. From the definition of norm, simple u plus v, inner product of u plus v. Apply additivity of the first lot, additivity of the second lot, what we get? Now I am applying first lot, inner product of u comma u plus v plus inner product of v comma u plus v. This is additivity of the first slot. Similarly, take additivity of the second slot. What we get? Norm of inner product of u comma u, inner product of u comma v, again inner product of v comma u, and also inner product of v comma v. This is additivity of the second slot. Okay. Now, you know that inner product of v comma u is nothing but v comma u. This is nothing but u and inner product of u comma u. And also they given inner product spec for any vectors for a scalar. This is 2 times of inner product of u comma v plus inner product of u comma v. Yes, this is actually by this can be written as, just now we know that what is a thing, you know that inner product of u comma v absolute is less than or equal to norm of u into norm of v, that is Cauchy-Schwarz inequality. From the Cauchy-Schwarz inequality, this is nothing but norm of u square. Okay, this is nothing but twice of norm of u into norm of u v. This is norm of v square. This is just like a square plus 2ab plus b square. Keep in mind, we are applying the result of C from the Cauchy-Schwarz inequality. What is that? Less than or equal to norm of u into norm of v. Therefore, this is nothing but norm of u plus norm of v whole square. This is actually, what's the left hand side I taken? Norm of u plus v whole square is less than or equal to this. That implies norm of u plus v is less than or equal to norm of u plus norm of v. This is called triangular inequality. It's very easy. Just you take, simplify, apply additive first slot and second slot, and simplify that. Use Cauchy's quasi inequality and simplify that, the fundamental a plus b whole square. Simplify that, automatically we get triangular inequality. I think it's clear for this. Yeah. Move to next orthonormal set. I think everyone is clear. These all four results and also what I discussed Pythagorean theorem, all the results they are going to ask any three results for 6 or 7 marks. Okay. Now move to orthonormal set. Yeah. In the previous class, we discussed what is orthogonal set. Now we are going to discussing orthonormal normal set. What's the difference between orthogonal and orthonormal set? Now here I am taking S having some set of vectors, say S having say V1, V2, etc. Vn. Having a set of vectors. These vectors is defined over a vector space, defined over a inner product space, over a set of real numbers. I consider S having orthonormal set. I am considering. What is orthonormal set? Means I have considered set of S having some set of vectors, say V1, V2, etc. Vn. These vectors are defined on inner product space V over a set of real numbers. Then S is called orthonormal set if inner product of Vi comma Vj equal to 0 for I is not equal to j equal to 1 for, this is extra thing compared to orthogonal set to orthonormal, equal to 1 for I is equal to j. Then we say that the corresponding set of vectors are orthonormal set. Orthogonal is only this much. Inner product of Vi comma Vj equal to 0 for I is not equal to j. Then set of vectors are called orthogonal set of vectors. So equal to 1, another extra condition I is equal to j means inner product of V1 comma V1, V2 comma V2 equal to 1. Then we say that the corresponding set of vectors are orthonormal set. This is a difference between orthogonal set and orthonormal set. Suppose these vectors are orthonormal non-zero set of vectors, these vectors form a orthonormal basis. What you know that orthogonal basis, extension of that is orthonormal basis. See, whenever you want to verify whether the given set of vectors are orthonormal basis, it is enough to verify the given set of vectors are orthonormal set of non-zero vectors. How we get? From the result what we discussed in the previous class. We discussed the previous class, suppose having S having n, say S is equal to V1, V2, etc. V1 set of n non-zero orthogonal set of vectors. We prove that S is a linearly independent and S is a basis for the inner product space over a set of real numbers. Means it's orthogonal basis. Now I extended that. Suppose the given set of vectors are orthonormal non-zero set of vectors over a inner product space of V over a set of real numbers, then that implies the given set of vector, the set of vector form a basis. What type of basis? Orthonormal basis. Keep in mind, if you want to verify that whether the given set of orthonormal basis or not, it is enough to verify that the given set of vectors are orthonormal set of non-zero vectors. This is extended from the result what you studied in the previous class, because this also very important in Gram-Schmidt process and QR factorization. Okay. Now this corresponding basis is called orthonormal basis. Now I am going to take one example for this. Show that the set S is equal to 1 by root 2 comma 1 by root 2 comma 0. Yeah. Better I to write set in the show that I'll write S dot T. Okay, fine. Show that S equals 1 by root 2 comma 1 by root 2 comma 0 is one vector, minus root 2 by 6, root 2 by 6, 2 root 2 by 6. The another vector is 2 by 3, comma minus 2 by 3, 1 by 3. These are the vectors. Show that is an orthonormal. Orthonormal basis of R power of 3 R, V3 of R, or V of R power of 3. All are same because each vector having components is 3. Okay, fine. Now I want to prove that means you have to verify whether the given set of vectors of S are orthonormal set of vectors of non-zero vectors. Yeah, definitely it's a non-zero vectors because at least one of the component of each of the vectors, say V1, this is V1, this is V2, this is V3, are non-zero. It is enough to verify whether it's an orthonormal set or not. How to verify that? First you have to verify that orthogonal set. Whether it's an orthogonal set means first you find out inner product of V1 comma V2. What is inner product of V1 comma V2 is V1 dot V2 because it's a row vector. 1 by root 2 into minus 1 by, if you want to write 1 by root 2 into minus root 2 by 6 plus 1 by root 2 into root 2 by 6. The last value 0 because multiplied with 0. Root 2 cancel 1 minus 1 by 6 plus 1 by 6. What we get actually 0. Next, inner product of V1 comma V3. What is inner product of V1 comma V3 is V1 dot V3 is nothing but what is V1? This is my V1. 1 by root 2 into 2 by 3. Okay. Minus 1 by root 2 into, plus into minus 2 by 3. The last value 0. These two are same is cancelled, we get 0. Next you take inner product of V2 comma V3. What is inner product of V2 comma V3? V2 dot V3. Dot product. What is V2? This is V2, this is V3. Minus root 2 by 6 into 2 by 3. Okay. The another value is plus root 2 by 6 into minus 2 by root 3. Yeah, V2 dot V3. Okay. Yeah. Minus 2 by 6 into what actually 2 by 3. Another value root 2 by 6 minus 2 by 3. Okay, fine. This value plus 2 root 2 by 6 into 1 by 2. See, observe carefully. 2 root 2. This is minus minus by 6. This is what actually 1 by 2 root 2. 2 root 2 by 6. Yeah. Then we have to simplify this. V2, V3, I have to simplify that. What we get actually? V2, V3. Now what we get actually? Now 2 is cancelled with 3. What we get? 9. Here also cancel with 3. Yeah. Well, now we get here minus 1 by V2, V3 is minus 2 by root 2 by 9. Means how we get actually 2 ones are 2 3s are what we get minus root 2 by 3 3s are 9. Here also 2 ones are 2 3s are what we get minus root 2 by 9. This is what actually minus here 2 ones are 2 3s are what we get plus root 2 by 9 minus 2 root 2 9. No, sorry, I did somewhere mistake here. Yeah, I did mistake here. Just a minute. Yeah, this is actually 3. Yeah, this is 3 actually. Yeah, 1 minute. Actually, overlook I written 2 root 2 by 6. Actually, this is 2 root 2 by 3. Not an issue. Inner product of V2 comma V2. While come to the last value, no, this is 0. Inner product of V1 comma V3, again this value. Yeah, not an issue for V1 comma V2 because 0 into any value is 0. That's why. Now while taking V2, V3, this is okay, fine, this is okay. While come to this third value of V2, this 2 root 2 by 3 into 1 by 3. Sorry, this is 3. Now what do we get? 2 is not cancelled here. 2 root 2 divided by 9. Sum of this equal to 0. After that, we are calculate. This is, now we say that S is an orthogonal non-zero, orthogonal set of non-zero vectors. Non-zero vectors. But I have to verify is orthonormal set. Therefore, I have to find out inner product of V1 comma V1. Means what? 1 by root 2 whole square. Square of each of the value plus 1 by root 2 whole square. What is that? Half plus is 1 because the last value is 0. Similarly, I have to calculate inner product of V2 comma V2. What is that? Minus root 2 by 6 whole square plus root 2 by 6 whole square, and also this value 2 root 2 divided by 3 whole square. Take that value. What is 2 by 36? 2 by 36, and this value is nothing but 4 2s are 88 by 9. Simplify that and then we get definitely 1. You take LCM, 36 is a LCM, okay. You need 2 plus 2 is 4, okay. Now 32. What we get? 36 by 36 equal to 1. Similarly, I calculate inner product of V3 comma V3. What is inner product of V3 comma V3? Square of each of the value. Yes. Now inner product of this is you have to inner product dot of this means 2 by 3 whole square. What is 2 by 3 whole square? Minus 2 by 3 whole square plus 1 by 3 whole square. Because V1 square plus V2 square plus V3 square. We have to dot product multiply the same component, we get the square of the value because same components V3 4 by 9 plus 1 by 9, we get 9 by 9, we get 1. Therefore, apart from this, inner product of V1 V2 V2 V3 V3 is 1. Therefore, S is an orthonormal set of non-zero vectors. Therefore, from that result, therefore, S is an orthonormal basis. Normal basis. What we discussed in the previous class, orthogonal basis, here orthonormal basis, because clearly this is a what the given set of vectors are non-zero vectors and also orthonormal set of vectors. Therefore, from that result, this is an orthonormal basis. Now onwards, keep in mind, if we want to verify orthonormal basis, it is enough to show that whether the corresponding set of vectors are orthonormal set of non-zero vectors. If you want to show that orthogonal basis, it is enough to show that the given set of vectors are orthogonal set of vectors of non-zero vectors that give rise corresponding basis. This is very easy, not necessary to verify that linearly independent, not necessary to verify S spans the corresponding inner product space. To avoid the thing, that's why that's a result is very, very important. Okay, you look into the few more problems in a textbook, you work it out. Now move to the different type of problem now based on the projection. Yes. Let if y is 7 and 6 and u is 4 and 2, find the orthogonal projection, I'll write it in the form of notation, orthogonal projection of y onto u, proj of y with respect to u, and the orthogonal set. Orthogonal set. Okay. Now, I want to find out proj of y with respect to u. Because why I have given so much importance for this in the further in QR factorization and Gram-Schmidt process and module 4 is very, very important. This. Now, inner product of y comma u divided by inner product of u comma u into u. Okay. First, you calculate what is inner product of y comma u. Yeah, they given in the form of column vector. What's the inner product definition? Y transpose into u. 7, 6, 4, 2. Multiply this. What we get? 28 plus 12. It's 40. Next, inner product of u comma u is nothing but u transpose into u. 4, 2, 4, 2. Square of that value. 16 plus 4, 20. Okay. Now, proj of y with respect to u is nothing but 40 divided by 20 into u. What is u? 4, 2. What do we get? 2. Take 2 inside the vector. Multiplied each of the component. Keep in mind, scalar, you know that inner product space, once you take, we have taken entire. Now we have to 4, 8 and 4. Next, you find the corresponding component. I have to find out the component, this orthogonal to orthogonal set. See, find the projection y with respect to u and also find orthogonal set. Means, I have to find out component of u is orthogonal to component of y orthogonal to u. Means, it is enough to find out what actually y y minus proj of y with respect to u. Means y minus y cap. Y minus y cap. What is y here? 7, 6. Okay. Minus, what's the proj of y with respect to 8, 4. What's the remaining? Minus 1 and 2. Subtract the vectors. You know, corresponding components have to subtract it. What is inner product of u? What is a u and y minus y cap? I have to verify it. It's nothing but u transpose. What is u transpose? U transpose into y minus y cap. Yes. What is u transpose? 4, 2. This is minus 1 and 2. Multiply it. What you are expecting? 0. Then only say that this is a component. Y minus y cap is a component, is a orthogonal to u. Minus 4 plus 2. Therefore, what's orthogonal set is? Orthogonal set is nothing but the orthogonal set is what actually? U. What is u? 4, 2. What is y minus proj of that value? 1, minus 1 and 2. Yeah, this way I have to find out orthogonal set. If you want to find out orthogonal set means you take the component of y, component of what about that proj of u with respect to u. That component, what component I find out, that component inner product value with respect to u must be 0. It is enough to find out y minus y cap, the component of y of orthogonal to what u, orthogonal to u. That is nothing but u minus y cap. Don't confuse, there we define u with respect to v with respect to u. Here instead of v you have y. Therefore, find the orthogonal set means it is first you find a proj value and find out the component of y of component y of the orthogonal of u. Orthogonal of u means y minus y cap. If you want to verify that inner product value is 0, therefore this is an orthogonal set. See, you know that what's the meaning of orthogonal set. Suppose you have a vectors, two vectors, the inner product value must be 0. Yeah. What are the two inner product values 0? These two. Therefore, this set is a orthogonal set. Keep in mind. Yeah. I think it's clear how to find out orthogonal set. Please, before going to write the solution of the problem, please look into the question, what they expecting. Based on that, please do it. Orthogonal set, you go come back to the orthogonal set. U and V is U and V having in a set. Inner product of U comma V must be 0. Then only say that that's orthogonal set. Now, how we get orthogonal set? You find out y minus y cap. You find the component of y of orthogonal of u is nothing but y minus y cap. What you taken u minus u cap. That inner product with u must be 0. Okay, this is a u y minus y cap set vector is a orthogonal set. Okay, now I'm going to take in the last problem based on this projection. Yeah, the last problem I'm not going to do fully because you already explained in this problem. Only the new thing I'm going to give a hint, you try and do it. Okay. U1 is 2, 5, minus 1. U2 is minus 2, 1, 1. And Y is 1, 2, 3. Verify the vectors, set of vector U1, U2, verify is an orthogonal basis for W is equal to span of W1 and W2, span of U1 comma U2. Alright, Y has the sum of a vector in W and a vector orthogonal to W. Yeah, first part you know that verify that this given vector U1 V2 is an orthogonal. It is enough to verify that inner product of U1 comma U2 must be 0. That is anyway U1 U2 are non-zero vectors and also orthogonal. Inner product you find out definitely we get orthogonal. Therefore U1 the set of vector U1 U2 is nothing but orthogonal vector of non-zero vectors. Therefore is form a orthogonal basis. Next, I want to find out what actually write Y as the sum of the vectors in W. What are the vectors in W? U1 and U2. But you already know that U1 and U2 set is a non-zero orthogonal set of vectors that form a orthogonal basis. Whenever this is orthogonal basis, how to express? Y can be written as C1 U1 plus C2 U2. Now, I want to find out C1 value. How to find out C1 value? What's the formula? C1 is nothing but Y comma U1 divided by inner product of U1 comma U1. I told already this is a formula we are taking to express linear combination of vectors of orthogonal basis vectors. And also what is C2? Inner product of Y comma U2 divided by inner product of U2 comma U2. You find out using these two and substitute. This is a way I have to do it. I am not going to do it on the board. You please find out these two values. Find out definitely we get C1 C2. For these values of C1 C2, now is possible to express Y. Once we get C1 C2, substitute the value and also substitute U2 U1 value. Now we say that Y can be expressed in terms of U1 U2 based on C1 C2. Using this formula, I have to find out. Because already I done such type of problem. After that, we want to express what actually write Y as a sum of the vectors in W Okay, that I explained. And a vector orthogonal to W means what? We want to find out after that y minus y cap. Y minus y cap you find out. Once we get y minus y cap, then you calculate, after once you calculate y minus y cap, you know how to calculate y minus y cap, you calculate it and verify it in a product of u1 comma y minus y cap, in a product of u2 comma y minus y cap. These two must be 0. These two must be 0. First you calculate y cap. Y cap means proj of y. With proj of y you have to calculate. You know that how to y, you get y, no? Y minus y cap. Y cap is easy to find out. You calculate it and do it. Y cap. How to find out y cap? The question. Y cap is nothing but sum of two vectors you have. Not only u means u1 and u2. The y cap is nothing but this. What you written y is y cap. You calculate and simplify that and take this. This inner product must be 0. And also you with u1 0, with u2 0 means inner product of u1 u2 y minus y cap 0. After that, observe carefully, y can be written as y cap plus of y minus y cap. You do it this. This part I'm going to leave it. I'm not going to do it on the board. Because I explained, I solved so many problems, you please do it. Okay. Suppose you don't get it. This worked in David Seeley textbook. This problem is worked in David Seeley textbook, you refer it. Okay. Because you already had done, why should I to do all the problems on the board? You please try and do it. I give a hint. First you find out this C1CT, express it and calculate this value, take the inner product, this value is 0, therefore this is orthogonal to W, and then we have to express y is y cap plus y minus y cap. Yes, this is a way I to do it. Yeah. In the next class, I'm going to discuss Gram-Schmidt process. Now I'm going to stop. Thank you very much to listening mind.